Okay, in today's session, we will discuss about torque slip characteristics of a three-phase induction motor. So we will try to derive the equation relating torque and slip, and based on that, we will draw the torque slip characteristics. Okay, so first of all, what is the basic working principle of a three-phase induction motor? Now, in the case of a three-phase induction motor, a balanced three-phase AC voltage is given to the stator winding, and it will produce a rotating magnetic field. And the speed of this rotating magnetic field, you call it as synchronous speed, and it is given by the equation Ns is equal to 120 F by P. Ns is equal to 120 F by P. Okay. Now, in this rotating magnetic field, the rotor conductors are placed. So, as per Faraday's laws of electromagnetic induction, what will happen? There is a change in the flux. So, an EMF will be induced in the rotor conductors. Now, this rotor circuit is closed. So, that means when an EMF is induced, a current will flow through the rotor conductors. So, there is an interaction between the current carrying rotor conductors and the rotating magnetic field, which will develop a torque. So, this is a basic working principle of a three-phase induction motor. Okay, now we will try to develop an equation for the torque. So, the torque of an induction motor, as I told you, it is due to the interaction between the current carrying rotor conductors and the stator field. Now, based on this, we will write the equation, that is torque is proportional to, we will write it as the torque developed by a three-phase induction motor is proportional to, the first one is the rotor conductors. They are carrying the current, that is rotor current I2. Next one is the stator flux phi, and the third one is the power factor. That is, because this is an AC machine, so we have to consider the power factor cos phi 2 also. So, considering all these terms, we can write the expression for the torque as torque is proportional to phi into I2 into cos phi 2. Okay. Now, we know that the induced EMF E2 is the induced EMF in the rotor conductors. This induced EMF E2, it is proportional to the flux, right? So, what we will do is, we will replace the term flux, that is phi, by the term E2. Okay. So, we can rewrite the equation as T is proportional to E2 I2 cos phi 2, where E2 is the induced EMF in the rotor, I2 is the current in the rotor, cos phi 2 is the power factor. Okay. Now, removing this proportionality constant, we can actually replace it by K. Okay. So, instead of this proportionality, we can write it as equal to a constant K. Okay. So, K is a constant. So, this is the expression for the rotor torque in the case of a three-phase induction motor, which is proportional to current, EMF and the power factor. Now, next we will try to derive expression for the torque under running condition. That means when the motor is operating under loaded condition, or when the rotor starts rotating. Okay, that time what will be the torque? So, again we are writing the same equation, that is torque is equal to K into E2 I2 cos phi 2. Now, we know the expression for this current I2 in the rotor conductor as well as cos phi 2. That is, while drawing the equivalent circuit of a three-phase induction motor, we have written expression for this current I2 and cos phi 2. So, what is current I2? Current I2 is given by S into E2 by Z2, that is E by Z, induced EMF by impedance. Okay, so what is Z2? Z2 is square root of R2 squared plus Sx2 the whole square. You can see here, in the case of rotor induced EMF, it is not just E2, it is SE2, because it depends on the slip frequency. Okay. Similarly, we can write an expression for the power factor cos phi 2 as R by Z. Okay, R by Z. That is why we are writing it as R2 by, what is Z? Square root of R2 squared plus S squared X squared. Okay, so now we will substitute these values, that is cos phi 2, the value of cos phi 2 and the value of I2 in which expression? In this expression. So, what is this expression? This is the expression for the rotor torque under running conditions. Okay. So, we will substitute that in equation number 1. Then what we will get? We will get it as torque is equal to K into E2 into, instead of I2, what we will substitute? This one. And instead of cos phi 2, we will substitute this expression. So, what is the final expression for the running torque? K into S is a slip, R2 is a rotor resistance, then square of the induced EMF by R2 squared plus S squared x squared. Now here you can see that this torque, that is torque under running conditions, we can write torque under running conditions, it is proportional to the induced EMF squared. Now this induced EMF, it is proportional to the supply voltage or the stator voltage V1. Okay, so this can be taken as a constant that we will see later. Okay, so now this is expression for the torque under running condition, which is depending on which all terms. It is depending on slip, rotor resistance, then induced EMF E2, then rotor reactance. Okay. Next, we will try to develop the expression for the starting torque, because we have to know each and every equation so that we can work out the problems. Okay. So what is expression for the starting torque? Now we already know the torque under running conditions, which is given by the expression T is equal to K into S into R2 into E2 squared by R2 squared plus S squared x2 squared. Now here if you replace this S is equal to 1, we will get the expression for the starting torque. So here you can see the starting torque equation, that is TST is equal to, this is equation, S is equal to 1. Okay. So TST, starting torque, is equal to K into R2 into E2 squared by R2 squared plus x2 squared. Now actually this equation we obtained from this particular equation by substituting the value slip is equal to 1. Okay, now we can further simplify this equation, because as I told you, this E2 squared is a constant. So why don't we combine these two, K into E2 squared, we will take it as a constant K1. Okay, so how did you get K1? K1 is equal to K into E2 squared. Now K1 is a new constant. Okay, so applying that, when we rewrite the equation, we will get it something like this. That is K1. What is K1? K into E2 squared. Okay, so TST is equal to K1 into R2 by R2 squared plus x2 squared. So I will write it here. Here K1 is equal to the constant K into E2 squared. The constant K into E2 squared. Okay. This is for just simplifying the equation. Now moving further. Now we will see the condition for maximum running torque. That is, under what condition maximum torque can be obtained in the case of a 3-phase induction motor. So that also we will start from the same equation for the running torque. So running torque is represented as TR. So this is expression, that is K into S into R2 E2 squared, and again as I told you, we will take this K and E2 squared, when multiplying we will take it as a constant K1, so we will get this expression. Okay, this is a simplified expression. Now in order to find the condition under which maximum torque will be developed, what we are going to do is we will just differentiate this equation with respect to slip, then equate it to 0. So we are differentiating this equation with respect to slip, that is why I am writing dTr by ds. So after finding the differentiative of this equation, this particular equation, I will equate it to 0, and finally I am getting this condition, that is R2 is equal to Sx2. That means when the slip is equal to the rotor resistance divided by rotor reactance, maximum torque will be obtained. Okay. So next step is this particular condition we will apply in this equation and see what will be the relation. Okay. So I am putting that in that equation. So we will get TR is proportional to SR2 by R2 squared plus S squared x2 squared. Here we are assuming that E2 is a constant. Okay, so that is why you cannot see that term E2 here. So here we are assuming E2 as constant. So you will get, instead of R2, I can write it as what? Instead of R2, I will substitute it as S into x2. Okay, so that is why I am getting the numerator as S squared into x2 by, in the denominator also, instead of R2, I will substitute from here S into x2. So finally what I am getting is the maximum torque is given by, it is proportional to 1 by 2x2, that is inversely proportional to the rotor reactance. Okay, that is expression which I am getting, that is maximum torque under running conditions. So if TR is the running condition, and just I put it as M to denote that is a maximum torque, I am getting it as proportional to 1 by 2x2, and while deriving this condition we assumed that E2 is constant. Now suppose if you are considering the term E2 also, then what will be the expression? The expression will be K into E2 squared by 2x2. Okay, so now what are the things which you understand from this expression? First thing what we can observe is that here in the expression for the maximum torque, we cannot find the rotor resistance, which means maximum torque is independent of the rotor circuit resistance R2, right? But the slip corresponding to the maximum torque, that is depending on the rotor resistance. See here, slip is depending on R2, but maximum torque is not depending on the rotor resistance. So the condition is that torque will become maximum when the rotor reactance becomes equal to the rotor resistance, which means by varying the rotor resistance, we can get maximum torque. Okay. Now, next thing is that I told you here we are considering the voltage or induced EMF V2, which is proportional to the supply voltage. So that means the maximum torque is directly varying as a square of the supply voltage. Okay. The next thing is how we can get maximum torque. Since it is proportional to inversely proportional, that is, since the maximum torque under running conditions is coming as inversely proportional to the reactance, what we can do is we have to keep the reactance very low, then the torque will be high. So what is X2? X2 is given by 2 pi into F into L2, where L2 is the inductance of the rotor winding. So that means if we keep the inductance of the rotor winding to the minimum value, then the reactance will be minimum and the torque will be maximum. So how can you keep this inductance to a minimum value? That is by reducing the air gap between the stator and the rotor. For that what we will do is, we will keep the rotor conductors very close to the surface of the rotor. Okay. So these are the conclusions we get after the derivation of that equation, that is the maximum torque under running condition. Now next question is how can you get the maximum torque, starting torque? The same equation, the condition is the same, but here we will get a slip S is equal to 1 because this is a starting torque. Starting condition, the speed NR of NR, that is the rotor speed is 0. That means slip S is equal to 1. So we have to apply that condition also, that is S is equal to 1. Also S is equal to R2 by X2, from which we will get the relation rotor resistance R2 is equal to X2. So the same condition we can apply in the equation, in the basic equation. So finally what we get the expression is K into E2 squared by 2 R2. This will be the expression. And this R2, how did you get this expression? Here we are substituting R2 is equal to, instead of X2 I put it as R2 and instead of S I put it as 1. Okay, like that we can do. Okay. Next, we will try to draw the torque slip characteristics of a three-phase induction motor. In the same graph, we can draw the torque speed characteristic also. We will just go through that. Now, for drawing any characteristics, first we have to get that relation between the quantities which we are going to plot. Here we are going to plot slip versus torque. Okay, so just to go through this equation. Torque is given by K into S into R2 E2 squared by R2 squared plus S squared X2 squared. This is a relation. Now let's case a first case. Suppose if the slip is 0. Okay, what is the meaning of slip is 0? Slip is 0 when NR is equal to NS, right? That is when the rotor speed is same as a synchronous speed, slip will be 0. So what will be the torque? So here just imagine if slip S is 0, what will be torque? Torque will also be 0, right? So let's just now see the characteristic. So this is the torque slip characteristics. Here you can see along the x-axis I have taken slip and along the y-axis torque is plotted. Okay. So now first point is this point where slip is equal to 0. We can see that at this point where slip is equal to 0, torque is also equal to 0. Okay. So this is the first point. Now we will take the second condition. What is the second condition? Just assume that the speed is very near to synchronous speed. It is not equal to synchronous speed, but the speed NR, that is speed of the rotor, is almost the same as that of synchronous speed, approximately equal to synchronous speed. That means slip value will be very low. S will be very small. If S is very low, what will be the value of S into X2? Because everywhere in the relation you can see this expression S into X2. This also will be very small. Okay, so it can be neglected when compared to R2. Compared to resistance R2, S X2 can be neglected because S is very small. Okay, now just assume that this R2 is also a constant. Okay, so just see the relation now. So we are ignoring this term, okay, and this is assumed to be a constant, that is R2, okay. This is S is here, K is here, and this E2 just assume that this is a constant. So finally the expression becomes T is directly proportional to slip, okay, because E2 is assumed to be constant, R2 is assumed to be constant, and Sx2 is very small. So torque becomes directly proportional to slip. That means when the slip is increasing from left side to right side, the torque will be something like a linear fashion, it will be increasing, something like this. Okay, so just again we will see that torque slip characteristics. See here, the second thing, that is torque is proportional to slip, is expressed in this portion. Here T is proportional to slip. Okay, now what is the next point? Next point is the point where we are getting the maximum torque. So this condition we know. In this condition, in order to obtain the maximum torque, the condition is S is equal to R2 by X2. So that condition we have learned. Okay, now just we will go through the next condition. So this is the third condition, that is when the slip is further increasing, when its value becomes like S is equal to R2 by X2, we will get the maximum torque. So now we got the maximum torque. Now the question is like, again suppose if we are trying to increase the slip. Okay, now again if we are going to increase the slip, what happens to the torque? It will not increase further, but it will decrease. The reason is there is a limit for this torque, right? After attaining the maximum torque, again if you are trying to increase the load, the speed will decrease. There will be a drop in the speed. That means the rotor speed NR will reduce. If NR is reducing, what will happen to the slip? Slip will become high, right? So the slip will become very high, and the value of S into X2, it will be very high when compared to the resistance R2. So that means now here we are going to ignore R2. So we are going to consider only Sx2, we are going to ignore R2. Okay, so just we will see that. So in this expression we are just ignoring R2, okay, and the value of S squared X2 we are assumed to be constant, okay. Okay, and this S will cancel. E2 is also assumed to be constant. So finally what we are getting is we will get as T is inversely proportional to the slip. That is, after attaining the maximum torque, if again we go on increasing the slip, due to the increase in the load, what will reduce? Rotor speed will reduce. When the rotor speed reduces, slip will increase. When the slip increases, S into X2 will increase. So R2 we can neglect. Okay, and if we assume X2 to be constant, finally the equation becomes K into S by S squared. So S and S will get cancelled, and finally what we get is torque is inversely proportional to the slip. See, this is the relation we will get applying this condition. Okay, now we will see that characteristic. So that is represented by this one, this portion. See here it is like a hyperbola, because here the relation between torque and slip is given by torque is proportional to 1 by S. Okay, so this is about the torque slip characteristics of a three-phase induction motor. Now here we have taken marked the slip from left to right, that is slip is increasing from here, from 0, then it is becoming like I put it as 25, 50, 70, like that. Okay, now when you are drawing the speed torque characteristics, what you have to draw is the x-axis, just to put the speed like this. The speed is increasing from right to left. Okay, so he can see that the speed is becoming, here the slip is 0. Okay, now the speed is increasing from right to left. You can draw like that. Now based on all these things, we will further analyze the torque equations, okay, because that is very important doing the problems. So the full load torque, starting torque, maximum torque, these three relations are very important. The full load torque is same like what we have written in the case of running torque equation. Okay, so it is given by SR2 by R2 squared plus SX2 the whole square. So this can be considered as equation for the full load torque, that is when the motor is loaded. Okay, when the motor is loaded on a running condition. Now what about the starting torque? We can derive the expression for the starting torque from this only, just to put S is equal to 1. Slip is equal to 1, because starting time rotor is not running, NR is 0, S is 1. Okay, so we will get this expression. Maximum torque condition we know, 1 by 2x2. Now what we are going to do is we are going to find some ratios. Ratio of maximum torque to full load torque, ratio of maximum torque to starting torque. It is very simple, no? We have the equation. Just Tm by Tf means 1 by 2x2 divided by Tf. Tf is also given as R2 by R2 squared plus Sx2 the whole square. So you are going to divide it. So when you divide it, we will get something like this. Then what we are doing is numerator and denominator, we will divide it by x2. Okay. So divided by x2 the whole squared, and finally the expression what you are getting is this. Okay. Here A, the constant A is given by R2 by x2, that is rotor resistance per phase by rotor reactance per phase. So this is the ratio of maximum torque to full load torque. Now the question is how we will find the ratio of maximum torque to starting torque. Very simple. In this equation put S is equal to 1. So you will get it as A squared plus 1 by 2A. What is A? A is equal to R2 by X2. So these equations can be used for doing problems. Okay. So let's just do 2 sample problems. This is the first one. Okay. Here it is given that an 8-pole 3-phase 50 Hz induction motor has a rotor resistance of 0.025 ohms per phase. So R2 is given. And this is a frequency F. And this is a pole, that means P. And the rotor standstill reactance is also given. That means X2 is also given. Now the question is like, at what speed is the torque maximum? Okay, so it is given that torque is maximum, but we are supposed to find the speed corresponding to this maximum torque. So first let's find the synchronous speed, ns 120 f by p. It's very easy, everything is given. Now what is the condition for the torque, maximum torque? R2 is equal to Sx2. Do you have a value of R2? Yes, R2 is given 0.025. What about X2? X2 is also given 0.15. Using that, we can find the expression for or value of slip. We will get it as 0.25. Always remember that the slip varies between 2% and 5%. That means 0.02 and 0. Like something like that. 2% and 5%. Okay. So just remember like that. Here it is given as 0.25. It is between 2% to 5%. Now, once we get the value of the slip, we can find the speed of the rotor. Speed of the rotor is denoted by the letter NR. Here you can see NR. So this is another expression. I will just mark this equation. That is NR is given by 1 minus S into NS. This is also a very important relation. Okay, so using this we can find the speed of the rotor. This is the question what they are asked. That is the speed corresponding to the maximum torque. Okay. Now moving further, the next portion what they have asked is what proportion as maximum torque is a starting torque. That means we have to find the ratio of starting torque and maximum torque. Okay. So we will find the ratio Ts by Tm. Okay. So Ts by Tm. Tm by Ts we know. What is it? A squared plus 1 by 2a. So Ts by Tm means you have to take the inverse of this. So 2a by a squared plus 1. Okay. So now A, how will you find? We know the rotor resistance and reactance. From that we can find the value of A and just substitute in this equation. And then we will get Ts, that is starting torque, is equal to 47% of maximum torque. That is 0.47 into maximum torque. So that is what is asked in the question. What proportion of maximum torque is the starting torque? Okay. So I hope that you understood this problem. Now we will try one more tutorial. A 4-pole P is given, 3-phase 50 Hz slip ring induction. It is a slip ring induction motor. So what is the difference between squirrel cage and slip ring induction motor? In the slip ring induction motor, the rotor circuit is not short circuited by these end rings. There are 3 terminals which can be taken out. It can be connected to some external resistance and thereby we can control the speed. So it is a 50 Hz slip ring induction motor rotates at 1440 rpm with the slip ring terminals short circuited. Rotor resistance is given. R2 is there and X2 is also there. Okay, so R2 is given, X2 is given. Now the question is, if an external resistance of 0.1 ohm per phase is added to the rotor circuit, this is possible only in the case of slip ring induction motor. You are adding an external resistance. Then what will be the speed? That means it is quite obvious, right? By adding an external resistance, speed can be changed. So they are asked to find the new speed. Okay. Now here, it is a very important point to note is that the load on the motor is not changed, the same load. That means the torque generated in both cases will be the same. That is the condition which we will be applying here. Okay, when we are adding an external resistance, the slip is going to change. Okay, accordingly the speed will also change, but the torque is going to be constant. So we will be equating two equations. One torque corresponding to the original slip and the second torque corresponding to the new slip. Okay, so first we will start with the synchronous speed. How can you find the value of the synchronous speed? That is given by ns is equal to 120 f by p. Okay, now we will find slip. How will you find slip? ns 1500 minus nr by ns. So we got the first value of the slip. This one we don't know, second slip. Okay, after adding the external resistance, we have to find the slip. Now what is the rotor resistance? Initially it was 0.1. Later on we added some external resistance, right? So now the new resistance, we will take it as R2 dash. It will be 0.1 plus 0.1, 0.2. How did you get this 0.1 plus 0.1? The original resistance R2 is 0.1. The additional resistance is also 0.1. So you will get it as 0.2. Now what we are going to do is we are going to write two equations related to the torque. So we will write the expression for the torque, that is 3 by 2 pi ns into S1 into E2 squared R2 by R2 squared plus S1 X2 squared. We know the value of X2, we know X2, we know the value of slip, everything we know. That E2 squared will just get cancelled. This one will get cancelled, and also these terms will get cancelled. Okay. So finally we are getting this expression, and here we are supposed to find the value of R2. Okay, S1, what about R2 dash? R2 dash also we found it to be 0.2 here. And equating that equations, finally we will get the value of slip S2 as 0.08. So that means by adding the external resistance, the slip is changed. So once the slip is changed, what will happen to the new speed of the rotor? Rotor speed will change according to the equation ns into 1 minus s. 1 minus, see here it is S2, the new slip. So you will get the speed. Okay. So I hope you understood what we have discussed today. Basically what we have discussed is like different expressions for the torque, the condition for maximum torque, then maximum torque under running condition, maximum starting torque. Then we discussed about the torque slip characteristics and about the different portions of that characteristics, why it is becoming linear, then why it is torque is further decreasing with increase in slip, we discussed. And also we discussed about the ratio of maximum torque to full load torque, maximum torque to starting torque, and also two sample problems. Okay, so just to go through this, and I hope you got somewhat idea about the topic.